Okay, next topic is flow lines. And let's look at this. First of all, R2 vector field, right? Two inputs creating a two-dimensional output. So R2 vector field. And in this case, we're going to learn how to estimate flow lines for this function, but I also want to talk to you about, this should actually be kind of familiar, maybe you don't recognize it, but you did spend some time in book 3 looking at the explicit function given here. And then we took partials, maybe an easy way to think about going from this line to this line to get the partial with respect to x is, this is actually the same thing as minus 3y x squared plus y squared plus 1 to the minus 1. And then you can do with respect to x, this is just going to be a general power rule times the power. So minus 1 times minus 3y is positive 3y down to power x squared plus y squared plus 1 to the minus 2. So it comes down in the denominator times the derivative of what's inside with respect to x, which is the 2x. So that's how we get the 6xy. Now partial with respect to y, you get to actually do some, in this case, you have to do quotient rules or product rule if you treated it this way. So a little more complicated, but again, this is a review. If you want to pause the video, make sure that you can take these partials to be prepared for the final. And if you put those partials together, you get the gradient vector, denoted like this. But we can also call it, it is a vector field, so we'll just use our notation f, but this capital F is the same as this gradient. And what we did back there when we had this particular example, you had a couple activities that asked you to get the path of steepest descent, the path that a raindrop would follow when it fell on this surface. So it's been a while, or you can go back to book 3 and look at some of the images, or just watch while I share the screen and we go to CalPlot 3D. So in CalPlot 3D, we can enter that function. Z is a function of xy, explicit function. And so I've entered that down here, negative 3y divided by x squared plus y squared plus 1. We get the surface shown here. And we had talked about, again, that there was this peak and this valley. We looked at that from the contour map perspective, but we also looked at it from the gradient vector field. And from the contour map, we were able to say, you did a homework activity assignment where you started at a particular point that I gave you, and you had to estimate the path of steepest descent, which of course is into this valley down here at the min. And you had to estimate, like if you started here, what sort of path would you follow? If you started over here, you would come around the back of this mountain and then come down into the valley. And that was a little tough for some of you, had some problems doing that from the contour map. And so this is to show you, you can think about that same problem, path of steepest descent, using vector fields. And so remember, the gradient creates a vector field, and the negative gradient, so I should actually put negative signs in here, is also a vector field, but it'll show us the path of steepest descent. So I'm going to put this gradient, negative gradient vector field, and in any arrow, it's showing you the path of steepest descent into the surface. So from both sides, it's a 2D one, so maybe it might make more sense to restrict it to 2D to turn off the surface. And so this is saying, had I started over here, let's say at the point 4, 2, I would follow this path. I can vector hop on the vector field and get down to the path, to the local min, following the path of steepest descent by following the negative gradient vector field. So I'm hopping from one negative gradient, one direction of steepest descent to the next as I move through the field. The more vectors you add, again, the less approximating you have to do. You can hop right to the next vector usually easily. You could start over here and again, same kind of thing. You get down into that min. These were maxes. This was a local max over here at right here at -1 along the y-axis. So had I started over on the sort of the side, the shallow part of that mountain, I'd have to come all the way around and then back into the min. So let's turn off the 2D anyway, just to get back to the surface, again, to show you that. So we were around the backside and came around, following the path of steepest descent. That path of steepest descent could have been obtained, and what we did back in book 3 was with the contour map. And so you would be at a particular point, you would move orthogonal to the level curves, and move your way right into the min, following against the direction of descent. So this is a negative 0.4, so I'd be moving, if I had started right here at this point, I move perpendicular, and this is the negative direction because I get to a negative 0.6, which is smaller. That was how you did it with a contour map. But now we can do that very same thing using the gradient vector field, in this case, the negative gradient vector field. Obviously, if I went back to the original, the positive gradient vector field is just taking all those vectors and reversing their order. Right, so now when I hit the enter, they go same pattern, but they go in the opposite direction. So steepest ascent would now ascend to that peak, which was over here, right here on the surface. Now we're in the min right here. Steepest ascent is while hiking out of that valley and around sort of the shallow part, sides of the mountain, up the hill, into the peak. So steepest ascent with the positive gradient field, steepest descent with a negative gradient field. Okay, and what we have done now, so I've shown you two ways to get a flow line, but we've done approximate flow lines. So you've visualized approximate flow lines by connecting them to an old idea, the perpendicular property of contour maps and level curves, or the new idea, connecting them to vector hopping. So to get these, you're just vector hopping through a vector field. No problem. So it's easy to estimate an approximate flow line, but notice that the flow line depends on the point that you're at, right? Remember that in that example we were just looking at in CalPlot 3D, right? The flow line starting here would bring me around like this. But had I started over at this point in quadrant 2, I'd come around this way, right? So the flow line depends on the point that you're at. Let's see. Next concept on flow lines is that CalPlot 3D can actually estimate these. And I believe you have to come over here to this XY plot. So you have a page in your journals that give you instructions as well. But I think you pick a point. Yeah, there we go. So you can move this point around and watch what happens to the flow line. I'm not sure why this flow line isn't continuing, but it's showing the point that originated at the top, 1.687, 2.62, 0. If you're at that point on the surface, this is the movement that you would move, which you have two ways of thinking about that. It is orthogonal to a level curve, but it's also vector hopping through the path of, in this case, steepest ascent, because we did the positive gradient. And this would continue on. Maybe I need to zoom out or in. It might show us. No. So play around moving this point and watching the flow line as it changes. Okay. So that is approximate flow lines, but of course now we're going to get into exact flow lines. And so there's a nice example. Pause the video and put this example up on the board. All right, next topic is exact flow lines. So pretty easy to get the approximate ones if you have a really good hand drawing or an excellent text tool that you've added enough granularity to your vector field. But how are we going to get exact ones, and what does it mean to be an exact flow line? So we'll start with this example. We want to show that this curve, what kind of curve? Plane curve or space curve? Plane curve, because it's an R2. The first component is movement in the X, the second component, movement in the Y. And we want to show that the flow lines for this R2 vector field are actually R2 plane curves given by this explicit formula. So this is a candidate for an exact flow line for this R2 vector field. Simple R2 vector field, 1x, you could graph this by hand. Pretty easy space curves, plane curves to draw too, just some nice parabolas. But it's okay if you didn't recognize those because we can see that from the tech tools. So let's actually look at the field and look at the space curves. Okay, so in CalPlot 3D, first thing I entered was let's turn these off and these off. So let's first talk about the vector field. So an R2 vector field, so I put the third component to be 0. I decided to keep those in blue, but again, you can change any color that you like for your vectors in the field. They automatically divided by 4. You don't have to do fixed length, so you can see that the things get a little steeper over here. And it is an R2 vector field, so I restricted the view to R2. We already had touched this XY plane, and then that picks a point and it shows you the flow line from different points, which again, that was pretty easy to do approximate, but we see that really what CalPlot3D is doing is vector hopping through that field to show the flow lines, and the flow line differs wherever you are on the curve. But our question was, in this example, we have explicit space curves that have this constant C. So I'm going to graph that plane curve for a particular constant C, and I think I've already done. Here's when I did C equal 2. So that is, let's go ahead and add a few things on that. Let's make that red, make it a constant color. Okay, so this red one is the plane curve, R of t equals t 1/2 t squared plus 2. Again, a parabola. Let's add another one in there. Let's maybe do when this is 1, the constant is 1. Let's click to add a color as well. Let's make that red, make it also a primary color. Okay, so those are our 2 space curves, plane curves, which we're saying, are those actually exact flow lines? They look like the shape given by the flow lines in this, right? They all look like parabolas, these flow lines, or parts of parabolas when we move over here. So it kind of makes sense that this might be a general formula for a flow line in this particular vector field. But how are we going to show that? So you see it visually, but we want to show that in algebraic sense. And so here's what the definition of a flow line is. You are a flow line. First of all, if you're a curve, if you're an R2 vector field, it must be an R2 plane curve. Okay, so we have a plane curve R of t. It will be a flow line for a vector field. So maybe we should say R2, and for an R2 vector field, f of xy, if this statement holds. Now let's think about this. This is saying that the derivative of your plane curve is the vector field at that point, t. So at a particular point, t, you have a plane curve. Ours were those parabolas. So I stop at a point on that parabola, and I get its derivative, which is just a tangent vector, right? That was from chapter 1 and chapter 2. So I have this parabola that represents the R of t plane curve. I stop at a particular t on that, compute a derivative. That gives me a direction vector. If that direction vector is the same as the vector field at that particular point. So I'm going to plug t in to get my x coordinate, t in to get my y coordinate. If the vector in the field at that point matches the tangent vector of your space curve, then you're a flow line. Well, let's again go back and think about what that means. Make sure we visually see that. Again, check it out. At any point on these red plane curves, you stop and you were to draw a tangent vector. And let's get this guy out of here. If you were to stop and draw a tangent vector there, it coincides with the vector in the vector field there. At every t along that space curve, that is the case. Again, you might want to add more blue vectors to your field, but you'll see that they always sync up, and so that the tangent vector at any point t on the red plane curve coincides with the vector in the vector field f at that point. All right, so it has to be the case. This is the condition that we have to check. So if they give you, which they have done in this example, this is really a candidate. They're saying, hey, is this actually the form of all the flow lines in this particular vector field? Turns out it is, and all we have to do is check this condition. So we have to take the derivative of our plane curve, 1t, and then we have to see what happens. So that's the left-hand side. Now the right-hand side, what is f of x of t, y of t? Well, x of t is t, y of t is 1/2 t squared plus c. So it's really saying what is t 1/2 t squared plus c. So if that was the input to your vector field, if x was t, y was 1/2 t squared plus c, plug that into the function, the vector function for your vector field, which this particular vector function says, oh, the first component is just 1, that's a constant, nothing changes. The second component is your x, which in this case is just t. They match, check. This is an exact flow line, the explicit equation of a flow line for this particular vector field. Now, let's rewind a little bit and talk about, well, we were given that as a candidate. So we didn't actually find an exact flow line, we checked if a candidate flow line actually was a flow line. Again, the check is just checking the condition of the definition, what it means to be a flow line. It turns out, though, to find exact, so again, we can check flow lines, but finding them, that's actually beyond the scope of this class, because it requires something called solving a system of differential equations. Another great math class, usually the next one, usually you're probably going to take a linear algebra and a differential equations following up on Calc 3. So you need some more math to be able to find exact flow lines explicitly. You'll work through some journal pages in this chapter where I show you how you might think about setting up the system, but you're never going to solve it. So you're going to do some partial integration to see if this might, if you can kind of manipulate things to try to come up with a candidate. And then what you can do, though, is check if a given candidate, if I just give you a plane curve or space curve, you can check whether it's a flow line. Which reminds me, we did this for R2, but you could also do an R3 example. I think maybe there's a good one. But yeah, so next one, also on the exact flow lines page. So for your exact flow lines page, we talked about this R2 one, but you could also ask it for R3. This is a 3-dimensional vector field plotted in R3. It would have an R3 space curve, R of t, and you could check if I gave you one. In this case, I'm giving you a helix, and I'm saying, is this actually, yes or no, is this actually a flow line? The equation of any flow line in this particular R3 vector field, we're wondering, and that's something you can check. Okay. Yeah, and then we talked about how you can use the tech tool CalPlot 3D to visualize approximate, and it's behind the scenes doing something like showing from that particular point vector hopping, but it could have the capability of solving systems of differential equations. It's not stuff you can do in a Calc 3 class. Okay, next topic we're going to come to in our next video is we'll return to where the other day we had some gradient vector fields in the corner. So we're going to return to those, and then we're going to talk about the next topic is work integrals, which are pretty neat because you have a vector field, the ones that we've shown on CalPlot 3D, the ones that you can visualize in 3-dimensional space. Maybe it's describing airflow in this room. Maybe it's describing flow of water in a pipe. You will be able to determine how much work is done to move a particle of a drop of water from one part of the pipe to another. How much work is done by the field. So those are work integrals, and they're coming.